Welcome back to the deep dive. Our mission today is really about solving this central, frustrating dilemma in modern AI-assisted development.
Right.
It's this constant trade-off between convenience and, well, true deep intelligence. You know the drill. You open your integrated AI coding assistant, you type a prompt.
And it just starts
It
immediately.
immediately starts trying to write code.
Yeah.
And that initial convenience, it's appealing, but we all know the goss.
Oh, absolutely.
For any task that spans more than, say, 2 files, that quick start it so often leads to frustrating hallucinations, endless cycles of debugging the AI's own mistakes.
And backtracking.
Yeah.
So much backtracking.
Exactly. And ultimately, your token budget just gets incinerated on, irrelevant code reads.
It's really the difference between asking for a simple patch versus attempting a large-scale refactor.
Okay.
On that small scale, convenience. It works. It's fine. But on the complex architectural scale, the default approach often feels like, trying to diagnose a networking failure by just staring at the closest blinking light.
That's a great analogy. You're fast, but you're completely blind to the overall system.
Exactly.
So today we were diving deep into a philosophy that really rejects that trade-off. It's called context over convenience.
And it's championed by a platform called Repo Prompt. The whole idea is to dramatically improve the quality, the accuracy, and the efficiency of the output you get from those truly high-reasoning models.
We're talking about the big ones, the architectural oracles of our time, like GPT 5.2 Pro and Claude 4.5.
Or Opus 4.5, yeah. And this isn't about replacing your favorite editor. That's a key point.
Yeah.
It's about giving your favorite models the perfect set of instructions, the perfect context they need to operate at their peak cognitive efficiency.
Okay, let's unpack this, because I'm going to take the skeptic's corner for a minute.
Please do.
We're developers. We value integration. We value speed. Tools like Cursor, Claude Code, they're integrated right into the IDE. They have built-in context awareness, fast tool selection. So why? Why would I, the developer, bother with an extra step for context building?
It feels like a step backward.
It does. Isn't manually curating context or waiting for some specialized agent to do it for me, isn't that just inherently a step backward in velocity?
That is the perfect question. It really hits on the resistance that, a lot of power users feel at first. And the core rebuttal is, well, it's simple, but it's also pretty profound.
Which is?
AI coding assistants are only as good as the context they are provided, period. And just as importantly, how efficiently that context is delivered. The default integrated approach, it fails because it prioritizes latency over comprehension.
Speed over understanding.
Exactly. Look at the 2 critical failures of this convenience approach. First, too little context means you get inevitable hallucinations. The model guesses at API structures, it invents methods, it completely misinterprets file relationships.
Been there.
We all have. Second, and this is just as costly, too much context means you're just wasting tokens on irrelevant code. If you're dealing with a code base with, say, 500 files, and the agent blindly tries to figure out which 5 files matter, that discovery phase alone can easily burn through 30,000 tokens of context that have absolutely zero relevance to the final implementation.
And crucially, that wastage. It's not just about the money, is it? It's about performance degradation, which I know we're going to get to.
It absolutely is.
So developers typically fall into one of 2 traps trying to solve this. They either manually copy-paste massive chunks of code, which is tedious, error-prone.
And you almost always miss a complex dependency somewhere else.
Right. Or the second trap.
Or they just rely on the integrated agent's broad search tools, like an embedded graph or a file search, and they just let the agent explore blindly.
And that blind exploration is what pollutes the model's context window.
It just fills it with noise. So Repo Prompt solves this by making the context process explicit and controlled. It gives you precise, granular control over the exact token-optimized context payload before the implementation phase even begins.
Okay, so that's our deep dive for today. We're focusing on how Repo Prompt delivers that precise control. We're going to explore 3 pillars that enable this structured workflow.
Right.
First, these incredible efficiency gains you can get through token-efficient context building using tools like code maps.
Then the cost optimization angle, which is huge, leveraging your existing flat rate subscriptions via CLI providers.
And third, the architectural unlock that comes from the MCP server, which turns Repo Prompt into this intelligent backend, an agent IDE, really, that external tools can tap into.
That's our roadmap. We're essentially going to demonstrate that for any complex task, moving past that perceived convenience and embracing a structured, context-first workflow It's really the only reliable path to superior results and maximizing the ROI on those powerful, expensive reasoning models.
All right, let's get into it. The agent orientation trap.
Let's start by defining why those quick, conventional agent workflows, the ones that feel fast, why they actually fail so dramatically when a task involves, cross-file logic or any kind of architectural change. We call this the agent orientation trap.
The agent orientation trap. Okay, walk us through a scenario so we can really understand what that means for an agent that's, operating inside a code base.
Okay, imagine you have a complex task. Something like refactor the payment processing module to support asynchronous webhooks and update the logging middleware across 3 different services.
A pretty standard, non-trivial task.
Exactly. When a standard integrated coding agent gets that prompt, it enters an immediate orientation phase. It doesn't magically know where the webhook handling lives, or what the service interfaces look like, or which files import the old logging function. It has no idea.
So it has to go looking.
So what does it do? It starts searching. It uses tool calls. Maybe it calls grep recursively on the secrec directory, just hoping to find payment or webhook. It reads the first 1,000 lines of the search results.
Which are probably mostly noise.
Mostly noise. It might then try to read the imports of the first file it found, discover a dependency, and start reading that file. It initiates changes based on this completely incomplete information, and then it often has to backtrack when it realizes it missed a critical interface definition that lives, 20 directories away.
And all of that, the searching, the reading, the tool calling, the failed attempts, it all just pollutes the context window, right? It degrades the model's focus.
Precisely, and we can quantify that pollution. The context window gets filled with noise. Things like the parameters for the tool calls themselves, like the grep command, the often massive, irrelevant text results from those broad searches, the internal system prompts that the editor needs just to function, and critically, the record of all the failed logical attempts and the internal backtracking the model does before it even shows you a single suggested change.
This is where we have to talk about context window size, because you hear these huge numbers being thrown around, 200K, 272K. I've even seen 1 million tokens advertised by some models. So why does using, say, 30K or 50K tokens for orientation matter so much if the overall window is that massive?
It matters because of the distinction between the advertised context window and what we call the effective context window.
Okay.
Models like GPT 5.2 Pro and Opus 4.5, they're reasoning powerhouses. They have these incredibly powerful, high-level synthesis and reasoning abilities. However, studies are showing that their highest quality, most reliable output, where they function as that architectural oracle, that happens in a kind of cognitive sweet spot.
And what's that sweet spot typically?
Typically, it's between 64K and 128K tokens, but only when the information is dense and highly relevant.
I see. So it's not just the size, it's the quality of the information in the window.
It's all about the quality. When you exceed that sweet spot, especially by front-loading the window with fragmented, noisy, and partially relevant discovery overhead, the model's high-level reasoning ability starts to degrade significantly.
So.
It starts making assumptions. It focuses disproportionately on information that's right at the beginning or the very end of the context, the classic lost in the middle problem.
Right.
And its ability to synthesize these complex cross-file relationships it diminishes.
So if the model spends the first half of its, let's call it intellectual budget, just navigating the file system, by the time it gets to the actual problem, the async payment refactor, its capacity for deep sound architecture is already shot.
That's a great way to put it.
It's like it moves from being an architect to being a code monkey, just fulfilling instructions without any structural foresight.
That's the perfect analogy. And the solution to that is the whole Repo Prompt philosophy. Thinking first, acting second.
Which basically means we are forcing the model to spend 100% of its initial thinking budget on the solution, not on figuring out what files it needs to read.
Exactly. By providing this complete, token-optimized, and curated context up front, we ensure the model enters the problem-solving phase with its full capacity focused on the high-level architecture, on dependency analysis, on considering edge cases.
And the time you save debugging and correcting all those hallucinations, it has to dramatically outweigh the perceived cost of that initial context curation step.
It does. It's not even close.
So this sounds less like an optional workflow and more like a mandatory structured approach for any real complexity.
It is.
If a task spans more than 2 or 3 files, you have to adopt this essential 2-step workflow: discovery, then implementation.
That is the rule. For power users who want reliable, architecturally sound results, that's the only way.
Okay, so let's detail those steps. Step 1, discovery. What are the context builder's marching orders here?
The context builder agent's role is purely research. And it has to be, this is key, non-opinionated. Its only job is to ingest the task description, explore the code base, even across multi-root repositories, and identify all the relevant files, understand their dependencies, and figure out their precise relationship to the task. It's essentially building the perfect, clean input payload for the next step.
And how does it do that? It's not just doing a text search, I assume?
No, absolutely not. It uses sophisticated tools, primarily tree sitter parsing, to understand the code structure, not just treat files as, plain text. This lets it make really intelligent decisions about which functions are affected and how to represent that context efficiently. And importantly, it doesn't propose a solution yet. It just gathers facts and prepares the data.
And then step 2 is the pivotal handoff.
Yes. Step 2 is plan and implement. So the final high-reasoning model, or GPT 5.2 Pro, receives a complete token-optimized handoff prompt from step 1.
And this prompt is structured.
Very structured. It contains the curated context, the files, the slices, the code maps, and a synthesized explanation of the file relationships. And because that context is complete and clean, the model completely bypasses that chaotic orientation phase and moves directly into architectural planning and implementation.
I'm really starting to see the value proposition now. The context builder ensures the plan is grounded in complete yet token-efficient context.
Right.
And then having that solid structured plan prevents the implementation agent from having to backtrack or reorient itself mid-task. It just maximizes its success rate.
The simple flow is now task right arrow but, context builder right arrow plan right arrow up, implement right arrow review.
Which replaces that chaotic orientation with a structured, efficient discovery.
And that ensures we maximize the effectiveness of every single highly expensive, high-reasoning model call.
All right, so if context is king, then token efficiency has to be the royal treasury.
Shuckles, that's a good way to put it.
Which brings us to how Repo Prompt protects that budget, because the skeptic in me is still a little worried. If this two-step workflow mandates, including the complete context, want my API costs to skyrocket, even if the result is better, how do we include more contextual information, the full picture, without escalating those costs and blowing past that effective $60K token budget?
That's where the engineering behind Repo Prompt's context selection becomes absolutely crucial. We're not just selecting files, we're selecting the mode in which that file's content is represented to the AI.
So it's fine-grained controlled?
Down to the individual file level.
And we have 3 modes for this, correct?
Yes. First, full content. This is reserved only for the very small set of files you're actively editing, where the model needs to understand the implementation logic perfectly to make precise line-by-line changes.
Okay, that makes sense.
Second, slices, which are targeted line ranges for medium context impact. And third, the real game changer for architectural context, code maps, which are reserved for reference files.
Okay, here's where it gets really interesting. Let's spend some serious time on code maps. Define what they are, technically, and more importantly, explain how they achieve that promised 10x token saving.
Code maps are brilliant. They leverage structural parsing tools like tree sitter to extract the high-level shape of the code, and they intentionally discard the implementation details.
The shape of the code, what does that mean exactly?
What the code map extracts is essentially the abstract syntax tree information, but presented in a very token-efficient text format. So you get function and method signatures, class definitions, type aliases, interface declarations, protocol headers, all the important structural stuff.
But not the logic inside the functions.
Exactly. Think of it this way. If you have a 1,000-line class file, 90% of that file is just implementation logic wrapped inside functions. The model needs to know that the class user manager exists and that it has a method called getUserById that takes a string and returns a user type. It absolutely does not need the 50 lines of database query, caching logic, and error handling that's inside that function, unless, of course, you're editing that specific function.
So the AI gets the API surface area and the structural definitions.
Precisely. And because the implementation details, the function bodies are discarded, that structural understanding achieves approximately a 10x token saving. A large 100 KB utility file might compress down into a 10 KB code map, providing all the necessary external reference points without any of the internal filler.
It's like giving the model the index and chapter headings of a book instead of the entire text, when all it needs to know is which chapters exist.
That's a perfect analogy.
Let's nail down a practical use case for our listener. Say I'm writing a new feature in my main application file, but I need to call 3 methods from a massive 5,000-line stable external API library that I'm not planning on editing.
Okay, perfect scenario. In that case, You would set your main application file to full content, and that 5,000-line external API library, you'd set that to code map.
Why?
The model needs to know the exact signatures from that library to prevent it from hallucinating functions, which is a super frequent source of errors. By using a code map, you provide that necessary high-fidelity structural context, and you could potentially include dozens of such reference files in your context window. You're providing a vast architectural view for maybe only 5,000 total tokens instead of the 50,000 plus tokens the full files would consume.
The documentation also mentions setting the code map mode to complete when you're asking purely architectural questions. What's the benefit there?
Right, setting code map mode to complete and selecting no files in full content mode is the ultimate architectural analysis configuration.
What does it do?
It tells Repo Prompt to gather the structural definitions from every single file in the currently loaded multi-root workspace. This gives the AI this incredible bird's eye view of the entire code base structure, all the definitions, all the imports, all the interfaces at a minimal token cost.
So if I'm asking GPT 5.2 Pro a macro level question like, identify all the places where we interact with the deprecated logger interface.
The model has the perfect structural context to answer that without ever reading a single line of a function body.
That structural view, combined with the power of a model like GPT 5.2 Pro, it seems like it could generate insights that even a single human engineer who's focused on one area of the code might miss.
It absolutely can. It completely bypasses the human cognitive bottleneck of having to hold hundreds of file structures in your working memory at the same time.
Okay, let's move on to slices. This seems to be the middle ground, right? For when code maps aren't enough, but the full file is just too much.
Exactly. Slices include only specific targeted line ranges, and they represent a medium token impact. They're critical because they are the operational mechanism for Context Builder 2.0.
What do you mean by that?
The Context Builder doesn't just decide which files are relevant. It decides which parts of the file are relevant.
Okay.
So for instance, if the Context Builder is analyzing a 2,000-line file, and through dependency analysis, it determines that only 3 specific functions are relevant to the task, maybe a setup function, a main handler, and an error reporter, it doesn't send the entire file.
It just pulls those out.
It automatically extracts those line ranges. It turns that 2,000-line file into maybe a 50-line slice containing just the relevant code blocks, complete with line numbers and the surrounding context like imports.
That is an immense efficiency gain. The Context Builder is basically performing this highly intelligent, task-specific compression before the prompt ever even hits the large model.
Correct. This dynamic slicing maximizes the efficiency of the token budget and ensures the model isn't forced to read through hundreds of lines of unrelated helper functions. It's intelligent filtering based on structural dependency, not just, a simple text search.
Speaking of budgets, we've mentioned this target of 60K tokens a few times. Why that specific number? Is that a hard limit on the models we're using?
So the 60K token budget, it's potentially an underestimation of the physical capacity of models like Opus 4.5 or GPT 5.2 Pro when you access them via an API, which can be 200K or even more.
Right.
But it's the default calibration point for power users who are utilizing the web interfaces, specifically the ChatGPT Pro web interface.
Okay, so it's a practical limit, not a technical one.
Exactly. That 60K figure represents the upper limit before users often start hitting these unexpected truncation or web interface errors when they're pasting very large structured prompts. This calibration just ensures that power users can consistently leverage the best model through its native, most easily accessible flat-rate platform without hitting those integration issues. It guarantees maximum reliability for that handoff prompt.
Okay, we've covered complexity within a single project, but modern development it's inherently multi-project. You have microservices, shared UI libraries, multiple related repositories managed as a monorepo or a set of sister repos.
That is precisely why multi-root workspaces are, they're non-negotiable for any serious development.
And most tools can't handle that.
Most AI tools are confined to a single project boundary, the root of the current Git repository. If your application relies on a shared utility library that lives in a completely separate repo, the standard agent is just blind to it.
But Repo Prompt isn't.
Repo Prompt lets you open multiple root folders, your application API, your shared data contract library, your worker microservice, all in a single workspace. And all the context features, including the context builder, code maps, file search, they all work seamlessly across these multiple routes.
So the agent can truly see the dependency graph between my main application and the shared library using code maps for the library, perhaps without me having to manually copy files or contexts across those project boundaries.
That's the crucial architectural unlock. It provides a unified, cross-repository context. This capability is absolutely vital for large organizations or monorepos. It lets you select a file from one repository and an interface definition from another and present a complete picture of that integration to the reasoning model in a single token-optimized prompt.
We've established the necessity of this two-step workflow, discovery, then planning and implementation. So now let's focus on the planning phase. This seems like the highest value step, but why is architectural planning so crucial? Why can't the agent just start implementing once it has all that curated context?
Skipping the planning phase is the quickest way to invite the agent orientation trap right back in, just, dressed in nicer clothes.
Of course.
An agent, even with perfect context, needs a clear, structured roadmap for the change. If you skip the planning, the implementation agent has to start making these structural and architectural choices on the fly, mid-sentence.
I see.
You might give it a product requirements document, a PRD, which describes what you want. Add feature flag support, for example. The architectural plan specifies the precise how.
So we will integrate the feature flag service client in file A, update interface B in the shared library, and conditionally render the UI component in file C. That level of detail.
Exactly that level. If those details are left to the coding agent, it has to dedicate its limited reasoning budget to structural design instead of focusing on implementation logic.
So this is where we use our best model to define the architecture and maximize the ROI on that powerful but expensive model call. This is where we bring in GPT 5.2 Pro as the architectural oracle.
Precisely. While there are a lot of excellent reasoning models out there, based on rigorous testing in complex environments, GPT 5.2 Pro is, for now, unmatched as the best planning model.
What are its unique advantages that make it so superior for this specific task?
Well, three things really stand out. First, its extended reasoning time. Unlike a lot of models that seem to rush to an output, GPT 5.2 Pro can actually think for many minutes on a complex problem.
And that's key.
It's critical. When you feed it 60K tokens of curated structural context, it has the time to thoroughly synthesize that information without prematurely collapsing the reasoning chain.
Okay, what's second?
Second is its thoroughness in analysis. It's just excellent at considering subtle implications, dependencies, and complex edge cases across that large context window. It doesn't just find a solution, it finds the best solution that respects the existing architecture.
And third,
It can effectively utilize the entire relevant code base, that full 60K of curated context, all at once during the planning stage. No other model right now provides that combination of capacity, logical consistency, and reasoning depth that's necessary to generate a truly sound architectural plan for complex tasks.
so the plan that it outputs has to be high quality, actionable, and structured. What are the mandatory components of a successful AI-generated architectural plan?
It needs to be definitive. First, a clear outcome specification, defining the success criteria, the expected behavior, the what. Second, a detailed architectural specification. This details exactly how the new code integrates, which structures are affected, the explicit dependencies, the structural how.
And the third piece is the most critical for the next stage, right?
Right. A sequential, ordered list of implementation steps. These have to be atomic, clear subtasks that you can individually verify. The implementing agent then simply follows this step-by-step roadmap, which reduces its cognitive load significantly.
Okay, so once that ironclad plan is in place, we move to implementation. The documentation outlines two distinct modes for this: XML Pro Edit and pair programming. Let's start with XML Pro Edit.
XML Pro Edit is an essential concept for reliable execution. It's based on a separation of concerns principle.
How so?
Reasoning models like GPT 5.2 Pro are phenomenal at the logic of a change, determining what needs to be changed and where. They are, however, often surprisingly bad at the mechanics of text manipulation.
Like what?
Handling exact indentation, managing line numbering during a block replacement, or correctly searching and replacing complex code blocks. They struggle with that.
So the model outputs a structured change format instead of trying to be a text editor itself.
Precisely. The model gets the full context, focuses its deep reasoning only on the logic, and then it outputs its changes in a structured XML format. It defines the start and end of the block to be replaced, inserted, or deleted. It might output a tag like changefile, scapeauth.ts type, replace start line 100 and line 105, and then the new code block.
And that XML output is then handled by what you call the delegate agents in Repo Prompt.
Correct. The XML is parsed by Repo Prompt, and these specialized, highly reliable delegate agents execute the mechanical file edits. They're designed to handle indentation, apply diff safely, they often operate in sandboxes, and they offer robust undo capabilities.
So it's a way to increase reliability.
Dramatically. It lets the deep reasoning model focus purely on the architectural synthesis, while the specialized tooling handles the file system and text manipulation with perfect precision.
That addresses complexity in single-phase changes. But when we talk about just sheer scale complex multi-phase changes spanning 10 or more files, that's where pair programming really shines.
Pair programming is designed specifically for that large scale. Its fundamental power is in exploiting what we call the two-context window advantage.
Two-context window advantage.
Right. It splits the cognitive load between two specialized entities. The workflow splits the roles between the driver agent, the high-level coordinator, something like Claude Code, and the chat implementer, which would be Repo Prompt Chat.
Okay, tell us how the driver and the implementer interact in this framework.
The driver agent is basically the project manager. It takes the overall architectural plan we generated, breaks it down into small, manageable implementation steps, and critically, it coordinates the context selection for each step using the MCP tools we'll discuss next.
Right.
It also handles the review and any error handling.
And the chat implementer is the worker bee.
Exactly. For every single small implementation step that the driver defines, the chat implementer receives a fresh, full context payload curated specifically for that mini task by the context builder.
So the critical insight here is that the chat implementer's context window never gets polluted.
Never.
It receives the cleanest possible context for the task at hand, implements it, and then it's ready for the next task with a totally clean slate.
Exactly. This avoids the chat implementer's context window from being compacted by unnecessary history or previous tool calls or irrelevant context from other phases of the project. It guarantees that for every small task in the overall plan, the implementing model sees the cleanest, most relevant context possible.
Which maximizes its performance and should drastically reduce iteration time and error rates.
It does. It's a powerful iterative loop. Plan, curate context, implement a single step, review, repeat.
Okay, this whole structured workflow relies on integration. Power users, they live in their favorite editors, Cursor, VS Code, whatever it is. If Repo Prompt holds all this context intelligence, the code maps, the slices, the multi-root awareness, how does the developer access it without leaving their preferred editor? That's where the MCP server comes in.
That's the core architectural layer. We use the Model Context Protocol, or MCP, which is an open standard designed to let AI tools communicate effectively with external services. Repo Prompt uses the MCP standard to transform itself into this specialized backend, an IDE for AI agents. It exposes its core advanced context management capabilities as a set of specialized tools that external MCP-compatible agents can control programmatically.
So if I'm using Claude Code, I can delegate the context selection for a large refactor to Repo Prompt's intelligence, all without leaving my Claude Code window.
Precisely. You get to keep your preferred UI and UX, the fast iteration cycles, the integrated chat, while leveraging Repo Prompt's specific intelligence, the cross-repository search, the code maps token efficiency, the AI-powered discovery. The MCP server provides a standardized way for those external editors to use these sophisticated capabilities through a suite of specialized MCP tools.
Let's highlight some of those key tools that really facilitate the superior context management beyond just, a basic file read.
A critical one is managed selection. An external agent recognizing a task needs high efficiency can call this tool and explicitly request Repo Prompt to add files using those token-efficient modes.
So it could ask for the main files in full content mode, but the dependencies in code map-only mode for that 10x token saving.
Or ask for a dependency file using slices mode for really targeted context.
That's true agency for the model. It's not just reading files, it's dynamically requesting how the context should be formatted for maximum efficiency.
Exactly.
What about that discovery step we mandated earlier?
That's handled by a tool called Discover Context. This is the delegation tool. The external agent provides the initial task description, and instead of searching blindly, it uses Discover Context to delegate the entire file selection process to Repo Prompt's context builder.
And Repo Prompt just takes over.
It runs its headless AI exploration across the multi-root workspace, uses tree sitter parsing to determine relevance, and then prepares the optimal token-budgeted handoff prompt package.
So you're delegating the most time-consuming, context-polluting part of the workflow, the discovery, to this specialized backend.
And that allows the coordinating agent to remain clean and focused.
And once the plan is executed and the changes are ready, how do they get back into the files safely and reliably, especially with these complex block replacements?
That's the Applied Its tool. This tool handles the final mechanical application of the plan. It manages complex search and replace operations or full file rewrites that the model generated. And since Repo Prompt controls the final write operation, it provides crucial safeguards.
Like what?
It offers an explicit diff visualization in the apply view for the developer to review. And most importantly, it provides full undo support via file checkpoints, which gives the developer a lot of confidence in the agent's complex work.
We have to pause here and talk about security. We're talking about tools interacting with high-value proprietary code bases, potentially across multiple repositories.
Absolutely. Security is paramount, and the architecture is designed for isolation. The MCP server primarily uses secure, local UNIX sockets for communication.
So all the traffic stays on your local machine.
Entirely local. It moves over a specialized protected communication channel, and no network ports are exposed to the outside world.
What about really strict environments, like corporate networks with zero network policies?
For those ultra-strict environments that might even block localhost TCP connections, there's an alternative file system transport mode. This uses file-based message passing for completely zero network communication, ensuring the context remains fully isolated within the machine.
And what about user oversight, preventing an agent from just running wild?
Every connection to the MCP server requires explicit user approval. You can allow less trusted clients, but workspace operations, especially high-risk ones like complex file manipulation or creating a new workspace, they trigger approval dialogues based on the associated risk level.
So there's always a human in the loop.
Human oversight is always the final gateway for any unauthorized or structural changes that are outside the developer's immediate purview.
Okay, now let's talk about the ultimate expression of this structured approach, the MCP builder workflow. This is where all that structural complexity disappears behind a single command. It's convenience, but built on a foundation of context.
The MCP builder workflow takes the entire complex process, discovery, planning, and implementation, and it stitches it into a single automated pipeline. And it's accessible via a simple /command like rpbuild within a connected agent like Claude Code.
So instead of manually running discovery, copying context, prompting for a plan, and then executing it, the connected agent just handles the whole cycle.
The entire cycle, end to end.
Walk us through the agent's logic when it gets that rpbuild command and the task description.
Okay, so the agent acts on the plan. First, it calls the Discover Context tool with the task description, delegating the context assembly. Repo Prompt returns the token-optimized context. Second, the agent takes that context and passes it to its strong reasoning model, say Opus 4.5, and prompts for the detailed architectural plan.
And then it implements that plan.
Third, once the plan with its ordered implementation steps is generated, the agent begins the implementation loop. For each step, it might call Manage Selection to ensure the implementing model has the most precise, clean context using slices or code maps. And finally, it uses the Applied Its tool to commit the changes based on the implementation step.
So it's an automated sequence that leverages all of Repo Prompt's best practices in one seamless pipeline.
Code maps, token optimization, dedicated planning models, all of it in one powerful, seamless pipeline.
One final crucial point on maximizing cost optimization, CLI providers. How does this fit into the structure, especially since we've talked so much about GPT 5.2 Pro being expensive?
CLI providers are a massive financial unlock. They let you use your existing flat-rate subscriptions, your Anthropic Max, your ChatGPT Plus Pro, your Google AI subscription, through tools like Claude Code and Codex CLI without incurring additional per-token API costs.
And that's especially valuable for the context builder workflow.
Hugely valuable. Discovery involves multiple file reads, searches, analysis calls, which can rapidly increase marginal API costs if you're paying per token. By routing that extensive discovery work through a CLI provider tied to your flat monthly subscription, you can run vast multi-route discovery for virtually zero marginal cost.
You're maximizing the ROI on your existing subscription commitment.
It's the difference between treating the discovery phase as this expensive, unpredictable expenditure and treating it as a fixed cost investment in quality.
All right, this brings us to model recommendations and optimizing that spend.
Based on the source documentation and, extensive testing, power users who adopt this context over convenience workflow really need to treat model pairing as a tactical decision.
So you're optimizing both spend and output quality.
You're building a specialized team of AI collaborators.
So we're not using one model for everything. We're matching the model's capability to the specific task complexity and the context constraints.
Precisely. We recommend a core trinity of models for the different stages.
Okay, let's hear them.
First, the best planning model is unequivocally GPT 5.2 Pro, accessed via a ChatGPT Pro subscription. It is the architect. You use it exclusively for that high-level architectural planning stage because its logical consistency and its ability to process that full 60K curated context are just unmatched.
Okay, the architect. What about the implementer?
Second, the best agent for the iterative implementation and review stages is Claude Code paired with Opus 4.5, accessed via an Anthropic Max subscription. Opus 4.5 really excels at following complex multi-step instructions and handling tool sequences. It's perfect for that pair programming loop where precision and adherence to the plan are key.
And third, the engine of the workflow.
The best context builder is Codex paired with GPT 5.2 Codex. This is a medium reasoning effort model, and it provides the best balance of speed and accuracy that you need for file exploration, for making intelligent judgments on file relevance, and efficiently managing the token budget during that intense discovery phase.
This tiered approach sounds like true workflow optimization. It ensures you only deploy your most expensive, most powerful reasoning model, GPT 5.2 Pro, for that high-value architectural planning task.
And you reserve the faster, more cost-effective models for the mechanical work of implementation and discovery.
That's the core of cost-effective LLM development, isn't it?
It is. Simple, isolated edits can be routed to ultra-cheap models like Gemini Flash 2.0 via an API.
Yeah.
But complex multi-file architectural changes must use the best reasoning models for planning, leveraging the context builder to ensure that those expensive model calls are never, ever wasted on inefficient discovery.
Finally, let's address the barrier to entry, the free versus pro feature set. What's the tipping point where a developer really has to move to the pro license?
The free tier is actually extremely valuable. It gives you basic file selection, chat mode, apply mode, and crucially the CLI providers, which lets you do that cost-effective use of existing subscriptions.
But
the pro license unlocks the foundational tools for large-scale token-efficient power usage.
And those essential power user features are what enable this entire philosophy, right?
Absolutely. You cannot reliably execute the context over convenience workflow without the pro features. These are code maps, which give you that 10x token saving you need for large code base analysis, the MCP server, which turns Repo Prompt into the agent IDE and lets external tools delegate context, and the context builder itself for that AI-powered discovery.
So for developers dealing with large code bases, complex refactors, multi-repository systems, Pro is basically a requirement.
For them, the Pro license provides the essential tools required to achieve superior, architecturally sound results without burning through vast quantities of tokens.
So what does this all mean for the modern developer? I mean, we've seen that maximizing AI output means moving past that initial convenience that's offered by the integrated editors, and instead embracing this structured, almost mandatory two-step workflow. Discovery first, followed by planning and implementation, the technical combination of code maps for massive token savings, context builder for intelligent discovery, and the MCP server for that dynamic agent integration. That is what allows these high-reasoning models like GPT 5.2 Pro to operate at their absolute peak efficiency.
And this entire discussion about perfect context synthesis, it leads to a really important question that challenges the traditional role of the human engineer.
Go on.
When a model like GPT 5.2 Pro is fed 60K tokens of curated structural context via code maps, it synthesizes a structural overview, an architectural blueprint, that a single engineer, limited by human working memory and their own localized focus, might genuinely lack, especially in a legacy or a large enterprise codebase.
So you're saying if the AI architect has a more complete structural overview of the entire affected codebase than the human peer does, that implies a fundamental shift in responsibility.
It does. The source notes that the engineer's role is to scope tasks and review changes. But if the AI provides a comprehensive plan that's grounded in the architecture of the entire code base, should the developer mindset evolve?
So should the engineer's primary role shift from creating the architecture from scratch to expertly validating the AI-generated architecture?
That's the question. Their job becomes refining, critiquing, and signing off on a plan that's proposed by a system that possesses a perfect structural understanding of the code. It's a compelling shift from creator to validator, leveraging the AI's perfect context synthesis as the foundation for all structural work.
A truly provocative thought to consider as these tools evolve. If you are ready to test this philosophy and gain that control over your token budget and your output quality, we highly encourage you to follow the quick win suggestion in the documentation.
It's a great place to start.
Download the tool, open a complex multi-file project, select a few files, and just copy your first prompt. You will immediately see how much cleaner and more structured the context payload is compared to a manual copy-paste. Then, make sure to set up a CLI provider to start leveraging those existing subscriptions cost-effectively.
Gain that precise control. Move from relying on blind convenience to demanding perfect context.
We'll catch you on the next deep dive.